Okay, I hope you can see my screen now. So today we'll talk about clustering. And I think before you do clustering, you really need to think about what it is you're looking for in your data. Is it just defining distinct cell types? It can be different versions of the same cell type, how they're responding to different stimuli or disease or whatever. It can be cell development. It can be stages in the cell cycle, spatial context. Really think about what it is you're looking for in your data before you start the analysis. And really to define what a cell type is, it can be there's a lot of different definitions, and you can have cell types and subtypes of the same cell type. And we often distinguish between cell type and cell state, where cell type could be T cell or CD4 T cell, but it can also be like infected, non-infective, active, inactive, different cell cycle stage, maybe not for the T cells. Apoptotic could also be a state that you can see also only due to technical reasons. So really think about what you expect from your data, but also keep an open mind that you might find things that you didn't expect, of course. So I will talk a bit about just basic clustering theory, go through some of the most common methods, and especially graph theory. And then talk about how we do single-cell RNA-seq clustering on graphs and a few other tools that I will mention. So basically, I think you all know the idea. We have our cells, we have our expression matrix of the cells, and we want to group them some way so that we can identify different cell populations. So the key things to consider when you do clustering is, as I said, what are you looking for? What is the cell type in this data? And what kind of cell types do I expect from this tissue? And how many clusters would I expect? And then there's a lot of choices you can do along the way. And we talked quite a lot about gene set selection. It's very important for dimensionality reduction. It's very important for integration, and it's very important, of course, then also for clustering. And we also need to define how we measure similarity between cells, and then also choose an algorithm to run the clustering with. And depending on what choices you make here, you will get different results. So it's really a matter of running something, interpret what you get. If it doesn't make sense, go back and think, what can I change to make it better? So what is clustering then? It's actually super simple. It's just grouping objects that are more similar than other objects in some way. And here are just a few commonly used methods. So the main idea is basically that the variance, well, my pointer is on the wrong screen. No, there we go. The variance within the cluster should be lower than the variance between clusters. That's also kind of intuitive, I think. So when we define the distance between cells, I think the highly variable genes is super important, because if it doesn't capture all your cell types, then you will not find those cell types. If you include too many variable genes, you might include a lot of noise and technical noise. You don't want batch effect genes. You don't want genes driven by quality of the cells and so on. And then, as I said before, it's quite commonly done in PCA space. But in principle, you could take UMAP but I think preferably a UMAP then in 10 dimensions or something. It's a really key consideration also, how many dimensions should we include? Should we use the first 10 or first 20 or 100 PCs? And how do you measure distance in that space? And Euclidean distance is by far the most common, but there's a lot of different options. Or sometimes also pairwise correlation. So the higher the correlation, the shorter distance. So you basically do 1- correlation. But there are a lot of more distances you can include and tweak and play around with. And I think this we've gone through pretty much before, how you select principal components. So I will skip through this. One thing I think most people that come from other fields are really used to doing bootstrapping when it comes to clustering. And bootstrapping is basically that you subset your data and you do clustering, and then you subset your data again and you do clustering, and you repeat it many iterations and see how consistent your clustering is. So basically then you can get p-values on your cluster, like this group of cells always end up in the same cluster. Unfortunately, in the single cell field, this is like completely forgotten. I've seen a few papers where they've done some bootstrapping in their supplement, probably because a reviewer asked for it. There's actually in Scran a function to bootstrap cluster, but it's very uncommon to see that people are bootstrapping. And I think a big reason is the computational cost when you start having very big data set and you're creating random sets and running it. But I think it would be good to see more bootstrapping also in this field, because it tells you a bit about how sensitive your data is to, like if you remove a few cells and you end up with very different clusters. So it's good to think about at least. So if you want to do clustering with Seurat, we first run find neighbors, which is the step where we create the KNN graph and then the SNN graph. So the default is to use PCA space, and it uses the Jacquard distance to create the SNN graph. And then of course, key things to think about is which reduction to use. Default setting is to use the PCA, but as Paulo said, if we did integration before, it might be harmony space or CCA space. The number of principal components, the K, so basically how many neighbors should we calculate in the KNN step, and then the prune setting. So the default is 1 divided by 15. But you can actually play around with this quite a lot and also get very different graphs and very different clustering results by tweaking the pruning parameters. But if you start pruning too much, you will get a lot of singleton cells that do not have any edges and just a single cell in a cluster.
Can I ask?
Yeah, go ahead.
About the bootstrapping.
Yeah.
If you have, because we had a discussion yesterday about the number of cells per cluster.
Mm-hmm.
So if you remove part of the cells and then you see a small cluster that disappears with the bootstrapping, should you also be worried then, or I mean, how do you?
No, I think, yeah, there is an issue. If you have too few cells, they will not stand out as a cluster. So I think it would be normal to expect that cluster to disappear if you remove half of your data.
But it doesn't still mean that the cell population doesn't exist, or I mean,
of course it doesn't. No, but if your larger clusters shifts quite a lot, then it's more of an issue, I would say, than the small ones. It's really hard to design good bootstrapping strategies also for single cell data, especially with this graph-based, because if it's hierarchical clustering and so on, it's a bit easier perhaps, because you have to recreate the graph each time if you're doing a proper bootstrapping, and then it will be so strongly affected by removing the neighbors. Then you'll have very few shared neighbors for that group, and then the Jaccard index will become low, and yeah, it's not super easy to do. Okay. And then after we create, sorry, the network, there's a function called find clusters. So it's basically this modularity optimization. And they have 4 different options for what algorithm to use. It's not super different, the results you get, regardless of which one you have. But you can, if you want to try out, oh, sorry. And I would say the main parameters to look at there is resolution and which algorithm you choose. So the resolution will decide how much you will cluster your data. So the higher the resolution, the more cluster, but smaller clusters you will get. And this is super hard to know where to stop, what resolution you should have for a specific data set. There's no one fits all. You should also be aware that it's not like hierarchical clustering, that if you change to different resolution, it will automatically just split one cluster into 2. Cells might actually shift clusters completely with a different resolution, because it's all built on these optimization algorithms that take different parameters into consideration. So it's not that easy that just because I increase the resolution, this cluster will fall into 2. It might actually shift your clusters quite a bit. Well, if we go to Scran, they have functions build KNN graph and build SNN graph. Actually, you don't really need to run the build KNN because the SNN will run both steps for you. And it just does very similar thing to Seurat, but also in some parts different. It doesn't do pruning. So in Seurat, they have this pruning parameter, while in Scran, they just add in edges when you have cells with a lot of shared neighbors. So normally when you go from the KNN to the SNN in Scran, you will increase the number of edges in your network, but they will also get a weight. And the default method is not the Jaccard index, but instead rank-based similarity measure between nodes. And as in Seurat, the important parameters is the use dimred in this case, with normally PCA, the K, and what type of weighting method. And then in Scran, they haven't really implemented their own community detection. Instead, you just take the graph you created with these build SNN or KNN graph, and you run the iGraph function. And that you can basically do also on Seurat. You can take the graph from Seurat and run another community detection method that exists in iGraph. So you can run cluster, Louvain, Leiden, Infomap, Walktrap. There's a bunch of those. The issue is that here it's not implemented a resolution parameter. So the only way to really tweak the number of clusters in Scran is to change the K parameter in your graph. And in ScamPy, they actually have not implemented any SNN. It's just a KNN graph. And they have a long list of different distance metrics you can use. So if you really want to play around with the distances, try it in ScamPy. And then they have just Leiden and Louvain implemented for clustering. And there you can also specify resolution. It's implemented more or less the same as in Seurat.